back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open. It's open mic on Science Fantastic. And just remember, we also report on the science news. Just recently, NASA sent the InSight Mars probe all the way out to the red planet. And by November, it should intercept the red planet and give us, well, a look at the inside of Mars. Now, we've photographed every single square mile of the Martian surface. We know more about the Martian surface than we do the planet Earth, for God's sake, and that's because the Earth is mainly covered with water. Mars is not. Therefore, we've been able to map every square foot of the surface of Mars, but we know nothing, I repeat, nothing about the inside of Mars. And that's where the Mars InSight probe comes from. It's part of the search to find out what's on the inside of Mars. We're going to sonogram Mars. Now, think of what a sonogram does. A sonogram sends sound waves into your body. The sound waves bounce off different organs, ricochet, cause echoes, and then a computer takes all these echoes and reassembles a picture of what's inside your body. In the same way, the InSight probe is going to detect Marsquakes. That's right, earthquakes on Mars. By analyzing Marsquakes will vibrate inside the surface of Mars, bounce off the different layers of, let's say, magma and the mantle of Mars, and allow computers to give us a rough approximation of the interior of Mars. Now, you might say to yourself, well, why should we care? I mean, that's just underneath tons and tons of rock. Well, it has to do with the mystery of the red planet. Why did Mars lose its water? Why did Mars become this barren, frozen desert? Mars was once tropical. It cooled off before the Earth did. Mars was tropical when the Earth was still molten. But something happened to Mars. Mars once had great oceans. It once had an ocean about the size of the United States of America. We see remnants of riverbeds and flows of rivers and the outlines of oceans. But now, nothing. What happened? Well, we think that Mars has no magnetic field, and as a consequence, there's no magnetic shield protecting it from harsh cosmic rays, and especially the solar wind, which blows the atmosphere into outer space. That's probably what happened to the atmosphere of Mars. And then the question is, well, can that happen to the Earth? Well, the answer is yes, but how? It turns out that our magnetic field is also beginning to wind down. That's right. If you go back to the ancient mariners, they recorded the strength of magnetic fields at different points of the Earth. And if you compare the strengths of the magnetic fields they found back then with the magnetic fields of today, we find that, yes, magnetic fields are dropping on the planet Earth. And believe it or not, we don't know why. That's right. We're clueless as to understanding why the magnetic field of the Earth is gradually diminishing. Now, that doesn't mean we're going to have a pole shift. That doesn't mean that we're going to have tremendous calamities like in the movies. No, this is the magnetic north that is decreasing in intensity. We don't know why. It has something to do with the churning of hot magma in the center of the Earth, but your guess is as good as mine. And so by analyzing the interior of Mars, we're going to begin to understand what's inside the red planet and what's in store for the planet Earth. Okay, well, let's move on now, and let's take a few listener phone calls. Let's take the first listener phone call.
My name is Patrick Keeley. I'm from Pittsburgh, Pennsylvania. And I was interested in how close theoretical physicists like you, Michio Kaku, are close to finding the theory of everything, or something close to the theory of everything.
Okay, well, let me take a stab at that question. First of all, since time immemorial, philosophers, scientists, and mystics have wanted to find the ultimate substance of reality. The Greeks, for example, got it down to 4. That is, earth, water, and dirt. And they thought that with four basic elements, they could create everything they see around us. When you look around you, you see the air, you see the oceans, you see water. But the ancients couldn't get anywhere with that theory. How do you explain the diversity of matter throughout the universe? How do we explain life? None of that could be explained by simply positing four substances. And then we had the Pythagoreans. The Pythagoreans worked out the laws of harmony. That's right. By looking at a lyre string, they were able to work out octaves, thirds, and fifths, and they reduced music to mathematics. And then they thought, aha, this is the theory of everything. This allows us to explain the universe. But it never went anywhere either. Because how do musical notes explain oxygen, hydrogen, helium? How do they explain the diversity of minerals and substances we see everywhere around the universe? Well, nothing much happened for a few thousand years until finally, in the 1800s, we had the birth of modern chemistry. With chemistry, we could reduce 100 or so elements, basic elements, out of which everything else could be formed. But that was also unsatisfying because why 100 elements? And there seemed to be regularities among these elements. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, you are listening to a program which talks about the cutting edge of science. And before the break, we had a call. How close are we to the theory of everything? Well, as you mentioned before, the ancients thought they had it all mapped out. They thought that there was an substance, a substance or thing out of which everything could be explained. Why do we have the oceans? Why do we have the air? Why do we have the earth? They thought that all the basic elements of the universe could be brought down to just a handful. But that theory never went anywhere. Then in the 1800s came the beginning of modern chemistry, and we began to reduce the enormous diversity of matter to just a little over 100. With about 100 elements, you could then explain everything else. But why 100? And why the regularity within the Mendeleev chart of chemical elements? Well, then we broke down the atoms and found there was something inside the atom. Atom means atom. A means cannot. Tum means cut. So atom means cannot cut. But we smashed the atom. With the work of Ernest Rutherford, the atom was not fundamental at all. We could smash the atoms and get even smaller subatomic particles like protons. Then we could smash protons and get even smaller subatomic particles. So when I was a grad student years ago, there were hundreds, thousands of subatomic particles. We were drowning in the theory of everything. How could Mother Nature be so malicious, so devilish, to create a universe where the fundamental substance of reality consisted of thousands of subatomic particles, each one with bizarre names, each one with bizarre subatomic properties? It couldn't be that way. Well, since then, we've made some progress. We have what is called the quark model, and the quark model can give you many of the other subatomic particles, but still we have 36 quarks. So the standard model of subatomic particles based on quarks cannot be the final theory. Some physicists say that it's a theory so ugly that only a mother could love it. That's the standard model, but it seems to work. Why should Mother Nature be so malicious? Because Einstein had a different point of view. Einstein was able to summarize the laws of matter, energy, and space and time into just a single equation. E equals mc squared, for example, unites matter with energy. M is matter, like the hydrogen of the sun, which turns into E of sunlight, which gives us Einstein's famous equation, E equals mc squared, which is the reason why the stars shine. And so the fundamental mystery of why the universe is lit up the way it is reduced to a single equation that's half an inch long. Well, Einstein thought that another equation, perhaps an inch long, would allow him to summarize all physical matter. Why do we have neutrons and protons and neutrinos? Why do we have all these subatomic particles with bizarre names? Why? Well, Einstein failed. He spent the last 30 years of his life, from 1925 to 1955, searching for this theory of everything. In fact, there's even a Hollywood movie which won the Academy Award featuring an actor who plays Stephen Hawking, my colleague, who recently passed away. The title of the movie is The Theory of Everything. Well, watching the movie, I thought it was a very good biography of Stephen. However, it never bothered to mention the name of the theory of everything. It is called string theory. Now, string theory is not confirmed. That's one reason among several that Stephen did not win the Nobel Prize. However, it is a theory which seems to summarize everything into the laws of music laid out by the Pythagoreans 2,000 years ago. They thought that the universe was made out of music, and all the musical notes corresponded to all the different kinds of substances that we see around us. Nice idea, but it never went anywhere. But now we have the atomic model of neutrons and protons and electrons. But where do they come from? We think that they, in turn, perhaps come from vibrating strings. So each note of a string is not a chemical. No. Each note of a string is a subatomic particle, which then can create atoms. And so why do we have so many subatomic particles? Because we have so many notes on a violin string. If you had a microscope, it can see right into a neutron or a proton. You would see that the neutron or the proton is not really a dot at all, as we once thought. It's really a vibrating rubber band. And when the vibrating rubber band vibrates at a different frequency, we call it by a different name. And that's why we have neutrons and protons and electrons. They're nothing but musical notes on a vibrating string. That explains the Standard Model. It explains why we have 36 quarks, why we have so many fundamental subatomic particles. They're not fundamental at all. And then physics is reduced to the laws of harmony of these strings. Chemistry is nothing but the melodies that we can play on strings. The universe is a symphony of strings. And then the mind of God that Einstein thought would reveal the deepest secrets of reality. The mind of God is cosmic music resonating through hyperspace. You see, these are not ordinary strings. These are strings that vibrate not in 3 dimensions, but in 11-dimensional hyperspace. And so, with this simple formulation, that music resonating through 11-dimensional hyperspace gives you all the subatomic particles we see in Mother Nature. And then the last question is, well, if this theory is so great, Smarty Pants, how come you guys don't win the Nobel Prize for it? Well, it's not verifiable at the present time. We have to build more particle accelerators, build more experimental apparatuses that can then prove that these particles do indeed arise from a string. So until then, sorry about that, it is just a theory. But if you want to know more about the theory, get a copy of my book, Parallel Worlds and also Hyperspace, which has a full discussion of the theory of everything. Oh, and lastly, some people say, give me an alternative. Let's say I don't like string theory. Let's say it's too crazy for me. 11-dimensional hyperspace sounds like Star Trek to me. Give me an alternative. Well, there is none. If you are a theoretical physicist, you know that this is the only game in town. Either you play with strings or you wander in the wilderness. There is no other alternative that has survived all the challenges made by physicists for the last 50 years. Think about that. Okay, let's move on now to the next listener phone call.
Hi, my name is James Heffernan, and I'm calling from Springfield, Illinois. No radio station, just Twitter. And I wanted to know, Elon Musk a number of times recently has stated that you can cause a runaway greenhouse reaction on Mars if you detonate a number of thermonuclear warheads over the southern ice cap. I wanted to know if this is possible, and also how many would it take, and why would only heat radiate down to the planet, and why would the ice not be irradiated? Thank you.
Well, first of all, you're absolutely right. Elon Musk is a pioneer who has the audacity to create a fleet of rockets that could reach the moon and perhaps even Mars, and he paid for it out of his own pocket. I mean, think about that. That would be once considered preposterous for a science fiction movie just a few decades ago. I mean, think about that. A billionaire who decides to finance a moon rocket from his own pocket. Amazing. Well, anyway, Elon Musk is this visionary who has business sense and has created a billion-dollar empire with Tesla Motors, PayPal, and now SpaceX. And he was asked a question. What's the fastest way to terraform Mars? Terraform Mars means turning it into a Garden of Eden, turning it into an Earth-like environment so that people can live and thrive on the red planet. And he said, well, yeah, detonate a few nukes on Mars. Well, some people thought that was an outlandish idea, so he backtracked a little bit. He says, well, let there be air bursts, not ground bursts, that would create radioactive fallout. So what is fallout? Fallout is radiation left over from radioactive dirt that is sucked into the fireball of a nuclear bomb, and also the irradiated vaporized remnants of the hull of the bomb casing. That's called fallout. However, if you have an airburst, that is, you detonate the bomb over the ground, there is no radioactive fallout at all. By the way, Hiroshima and Nagasaki were both airbursts. Many people say, well, let's take a short commercial break and then let's continue a discussion of nuking Mars. Is that the best way to make Mars into a Garden of Eden? Science Fantastic with Professor Michio Kaku. Well, before the break, we had a very interesting phone call asking about Elon Musk's idea of, well, nuking Mars. Elon Musk is the great scientific visionary and billionaire pioneering SpaceX, Tesla Motors, and PayPal. And he has created his own moon rocket called the Falcon Heavy and even has a Mars rocket on the books. It's called the BFR, this gigantic rocket that takes us to Mars. B is for big, R is for rocket, and F is for your imagination. Well, in spite of all the difficulties, he does believe that our future lies on the red planet. But how do you turn the red planet into a Garden of Eden? Well, nuke the ice caps. Mars has two gigantic polar ice caps that are full of carbon dioxide and water in frozen form, so why not melt them? Well, at first he said nuke Mars, but then he began to backtrack when he was criticized, and then said, well, why not have an air burst? So let me explain. Where does the fallout come from an atomic bomb? It comes from radioactive dirt that is sucked into the fireball, and also the bomb casing, which is vaporized in the process of detonating a atomic or hydrogen warhead. But you see, Nagasaki and Hiroshima, those bombs had very little fallout. Now, some people say, it means that even after a nuclear war, we can recover very quickly. Well, not so fast. It turns out that, they were airbursts, which meant that their fallout was diminished. However, if they were ground bursts, then they would be radioactive for decades to perhaps centuries to come. But because they were airbursts, it reduced the amount of fallout that was sucked into the fireball. So Elon Musk says, let there be airbursts over the surface of Mars. Well, personally, I think there's a better way to do it, and that is to have solar satellites. Solar satellites orbit Mars to beam down solar energy that would then slowly melt the polar ice caps without having to radiate Mars. Is it possible to nuke Mars? The answer is yes. Nuclear weapons are cheaper than you realize. They only cost a few $1 million a piece. Believe it or not, they can be mass-produced. Of course, to obtain one is quite difficult. But the actual physical cost of creating a hydrogen warhead is actually not that much because most of it is automated and mass-produced. So it is possible to nuke Mars, but the consequences, well, there could be unexpected consequences. We don't know the stability of the red planet's polar ice caps. We don't know how many bombs are necessary to accomplish that feat. It's basically a shot in the dark. And personally, I think that astronauts may not want to drink water that comes from the polar ice caps if the water makes you glow at night all by yourself. And so I think that is not such a good idea, especially when there are alternatives to terraforming Mars. In my book, The Future of Humanity, I mentioned that if we can raise the temperature of Mars by 6 degrees, 6 degrees, if we could raise the temperature by that amount, you would have a runaway greenhouse effect all by itself, and Mars would literally terraform itself. Now, you may say to yourself, isn't that science fiction? Well, yeah, part science fiction, but realize that we are terraforming the Earth right now. That's right. We are terraforming a planet, except that planet is not Mars. It happens to be the planet Earth. And so we do have some experience with terraforming a planet because we are terraforming our own backyard. And, well, who knows what's going to happen to our planet as a consequence. Okay, let's move on now to the next listener phone call.
Hello, my name is Ed. I'm calling from Fairbanks, Alaska, radio station KFBX. And I was wondering what the shape of Hawaii is as the lava comes up through the ocean, up over the top of the ocean. And as it spills out, does it form a mushroom? Are people more or less living on the sides of a mushroom that could break off on a heavy earthquake and then fall into the ocean? Thank you.
Well, you ask a question that's on a lot of people's mind right now because of the devastation in Hawaii. In fact, I once took a helicopter rented by BBC Television, and we filmed. We actually filmed right over the Kilauea volcano, which is now erupting. And very clearly, from the vantage point of our helicopter, you could see the red-hot molten lava spewing out, creating this gigantic volcanic dome. So you're right that the emission of hot magma from the bowels of the Earth do create this cone, which creates the cone of the volcano. And I should also point out that, yes, we have all the devastation, the evacuations, the chaos caused by this, but realize that, well, the Hawaiian Islands themselves are a lesson in geology. You see, a new Hawaiian island is being created even as we speak. That's right. Even as we speak, a new Hawaiian island is erupting off the coast of Hawaii, creating the next Hawaiian island. Now, if you take a look at a map of the Hawaiian Islands, you see that they're like a bunch of dots lined up in a row. Now, why is that? Why do we have all these volcanoes lined up in a straight line? And the answer is very simple. Continental drift. It turns out there's a stationary pool of magma right there, but as the Earth's crust moves over the stationary pool of magma, the magma's pressure eventually punches a hole through the crust of the Earth, creating the next volcano. And that's the origin of the Hawaiian Islands, the fact that continental drift is pushing the crust of the Earth over a stationary pool of magma, which periodically punches a hole, creating the next Hawaiian island. Now, believe it or not, we also find that on Mars. Yep, on Mars. On Mars, there are 3 volcanoes lined up in a straight line, just like we see here on the planet Earth in the Hawaiian Islands. So even though Mars probably does not have continental drift today, we think that in the past it probably did. And that's the reason why we have 3 volcanoes right in a line in Mars, just like we see the Hawaiian Islands today, because basically we're seeing geology at work. And then the next question is, well, where does all this energy come from? Let's take a short commercial break, and after the break, I'll tell you where the energy of all this activity in Hawaii come from. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question about volcanoes, given the fact we had this massive eruption taking place in the Big Island of Hawaii with the Kilauea volcano, causing people to evacuate from their homes. And we left off with the question, well, where does all this energy come from? Well, believe it or not, there was a debate 100 years ago which split the scientific community. Biologists and geologists said that it must have taken literally billions of years to create the planet Earth. However, physicists said no. It only takes a few million years for molten rock to cool down. The Earth is still hot. Therefore, the Earth must be just a few million years old, not billions of years old. Well, here was one example of when we physicists were wrong. That's right. We got the laws of physics wrong. Madame Curie was the one who got it right. Madame Curie said radiation, like coming from thorium and uranium, they can be radioactive for billions of years, and that's why the volcanoes that we see in Hawaii are erupting. The center of the Earth is radioactive with uranium, thorium, and other radioactive chemicals. That generates heat for billions of years. The Earth should have cooled down by itself millions of years after it was formed, but that's because ordinary heat cannot be sustained for billions of years. Radiation can. And so here's an example of, well, where we physicists were incorrect. The Earth is radioactive. Radioactive elements can be radioactive for billions of years, not millions of years. Okay, well, let's move on to the next listener phone call.
My name is Victor, and I'm from the great city of Detroit. My question is, a lot of science people poke fun, saying I'm supposed to believe in some magical wizard with a long beard created life. I say no, absolutely not. Some greater power must have caused the universe to exist. The existence of a watch indicates the presence of an intelligent mind, right? And the existence of the universe and various phenomenals within it indicates the presence of even a greater intelligence, right? The universe looks the same whether science admits there's a God or not. So why not be logical and say science is non-religious, but we think there is a creator, instead of laughing at believers who also trust science? Please get back to me on this. Thank you.
Well, of course, you asked the $64,000 question of, is there a plan or a design, or if so, is there a designer and a planner that created everything? I don't have time to discuss everything. However, in my book, Parallel Worlds, I do give you the philosophy that Einstein laid out, that first of all, there are two kinds of God that we have to be very careful to distinguish. The first God is the personal God. That is the God that answers prayers. Every Christmas, kids pray to God to get that shiny bicycle they've always dreamt about. Other people dream about smiting the Philistines. Other people dream about glory. But whatever, we have the personal God, the God that answers your prayers. Then we have the God of Spinoza, the God of order, the God of harmony, beauty, simplicity. Einstein did not believe in the God that answers your prayers. Why should the God of the universe, which created the glorious heavens, be concerned about that red bicycle that you want for Christmas? He thought instead there should be a creator a la Spinoza's creator. That is, the laws of physics are so beautiful, he thought. They're so simple and so elegant that it could not have been an accident. So he believed in what is called the Old One. In many of his letters, he talks about the Old One, because the universe, of course, is very old. But where did it all come from, this ancient universe of ours? And he considered himself a child entering a library for the first time. Think of entering a gigantic library with thousands of books, and all he could do was take the first volume and open the first page and read the first chapter in this gigantic library called the universe. And so Einstein did not think it was an accident, but he did not believe in a personal God. He believed in the God of simplicity, order, the God that gave us a harmonious universe when the universe could have been random. The universe could have been ugly. It could have been, for example, a universe without stable matter. So the universe would be nothing but a sea of electrons and neutrinos and not much else. But here we are with this glorious universe, with this incredible diversity of chemicals and life forms and substances, this incredible diversity of forms, and it didn't have to be that way. And so that's what Einstein thought about this. And then the next question is, what about religion as an organized institution in science? Well, Galileo, I think, said it best. Galileo said that the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So, in other words, religion is about ethics. It's about how to be a good person, how to be God-fearing. It's how to be kind to your neighbors. It's the golden rule. All that is contained within the Bible. However, we also have the laws of physics about how the heavens go. And Einstein thought we should keep the two distinct. And the trouble occurs when religious people pontificate about natural law or when scientists begin to pontificate about ethics. That's where we get into trouble. Okay, well, let's move right along now to the next listener phone call.
Hi, this is Armand. I listen to you on YouTube, and I'm from Queens, New York. My question is, what is the story with invisibility? I remember you talking about it a while ago. You said you didn't think it was possible, but then it was. What's the update? I want to know more about that. And do you think it's possible, physically possible, to create a lightsaber? Because I love Star Wars. Have a great day. Love your show. You're the best.
Okay, well, first of all, invisibility, yes, it's possible. Is it practical? Well, we're not quite sure yet, but we now have a theory of invisibility. I should also point out that the idea of invisibility has fascinated philosophers for thousands of years. Did you know that Plato, the great Greek philosopher over 2,000 years ago, wrote an essay about invisibility? He said that if somebody were to find the secret of invisibility, they could enter the king's castle, they could kill the king, take over the queen, and become the next ruler. So that invisibility, if it were possible, could unleash all our baser instincts. And then he began to wonder whether or not we humans are fit to rule if we have the secret of invisibility, because all sorts of chaos would erupt as a consequence. And so he used that as a moral example to test how far can humans become evil if they have this magic of invisibility. And then, of course, we have Harry Potter with the invisibility cloak. And the idea then is not so recent, but the question is it possible? And the answer is yes, but let's put some caveats. First of all, we now have something called metamaterials, and guess who's funding research on metamaterials? The United States Pentagon. Duh. I mean, the Pentagon would be negligent if it didn't support research on metamaterials. Now, think of a river. If you have a boulder in the middle of the river, water goes around the boulder, reforms at the other end, so that if you're downstream of the boulder, you don't know there's a boulder upstream. For all intents and purposes, the boulder is invisible to you. Now replace the stream with light. If light can somehow wrap around a boulder, reform at the other end, then downwind of the boulder is invisible. If you look upstream, what do you see? You see light coming at you from before the boulder, because the boulder's light breaks up, reforms at the other end, and the boulder's light becomes invisible. This is called metamaterials, and there's something called the index of refraction. The index of refraction measures roughly how much bending there is as light goes through glass, as light goes through a diamond, as light goes through water, or even air. It turns out that the index of refraction is usually greater than 1. That's why we have telescopes. That's why we have microscopes. That's why the retina of your eye can see, because all of these things have an index of refraction greater than 1. But what happens when it's less than 0? Chaos erupts, and we'll talk about that after the break. So after the break, we're going to talk about invisibility. Is it possible? Yes. Is it practical? Nobody knows. Welcome back to Science Fantastic with Professor Michio Kaku. Well, the caller that just called in asked about invisibility, something that is very ancient, and Plato himself, the Greek philosopher 2,000 years ago, mused about invisibility. He wanted to know whether men are moral enough to handle a volatile technology like invisibility. And he thought to himself and he said, nope, men are too greedy. We're too selfish, that if we have the power of invisibility, that we can steal things and not get caught, we can kill people and not get caught, then we would kill the king, become the next king, take the queen, and become the next ruler. Chaos might erupt if everybody had an invisibility shield, because then we could settle our scores and kill people that we don't particularly care for. He thought that humans are simply not moral enough to handle a technology like invisibility. Well, as I mentioned, now we know that invisibility is in principle possible. There's something called metamaterials, materials that are quite exotic but make things impossible to see. Just like a rock in a river becomes invisible downstream, it turns out that light can bend around a metamaterial, reform at the other end, just as if the object in the river is not there at all. Now, we've actually tested it with microwaves. I have a video where we shoot microwave radiation around metamaterials, reforms at the other end, and bingo, it disappears under microwave. But hey, we don't have microwave eyes. We have visible light eyes. We want to do it with color. We want to do it with ordinary light. But there's a problem there. You see, the wavelength of microwaves could be a few inches. The wavelength of light is measured in billionths of a meter. In fact, we're talking about atomic scales when we're talking about the wavelength of light. And so you would have to create a metamaterial that could bend light at the distance of molecules, and that does not yet exist. Again, it is possible on paper that if you could create an object with an index of refraction less than 0, it would in fact bend light in a way that is physically impossible, but would make possible invisibility. Now, you may say to yourself, well, doesn't the Pentagon already have invisibility in the form of stealth bombers? Well, the answer is no. Stealth bombers are not invisible. You can see them very clearly with the naked eye. However, under radar, they have a very small radar image about the size of a bird, and therefore, for all intents and purposes, the airplane becomes invisible. Now, how does the military do it? When radar hits a surface, it bounces, and that's how we know the object is there, by analyzing the bounce. However, if you can attenuate, diminish the amount that bounces back, then for all intents and purposes, the object is invisible under radar. There is no echo when you shoot an object on a stealth bomber with radar. You can do this using a series of tricks. You can use certain materials that diffuse radar signals. You can also cut corners, make it smoother. So that's why stealth bombers' shape are so weird looking, because they're shaped the way that maximizes the dispersion of radar signals. Bingo, that's called a stealth bomber. However, a true invisible bomber would have to be made out of materials that can bend light on the distance of atoms. And that's where the problem lies. We have not been able to do that at the present time. We can do it for microwaves. In principle, we can do it. We've already done it for microwaves. But microwaves have a wavelength measured in inches. We want a wavelength measured in billionths of a meter, like ordinary light. And we have not done that yet. So, in other words, it is possible to make an object invisible on paper. But in reality, it requires a new substance called metamaterials that we have not yet invented. However, there is hope. We now have something called nanotechnology, which precisely creates materials at the atomic scale. So, in other words, in principle, we could use nanotechnology to create atomic machines that would then create, atom for atom, an object whose ability is to create bending of light with an index of refraction less than 0. If you could put all those ingredients together, bingo, you would have invisibility. Does it exist yet? No. We do not yet have a nanotechnological substance that can bend light like a metamaterial. It is possible, but it's simply too hard to do with present-day technology. So, well, sorry about that. Okay, let's move on to the next listener phone call.
Hello, Michio. My name is Scott Johnson. I'm from Magnolia, Ohio. I'm not listening to a radio station. But my question is, if most of the galaxies in the known universe contain within them a supermassive black hole, and the result of the energy being expelled from these singularities is a quasar, could the Big Bang be from a super astronomically large quasar, from a huge black hole? Thank you.
Well, the short answer is yes. There is a relationship between the black hole and the Big Bang, and some astronomers have even written articles saying that perhaps the universe is a black hole. Now, that sounds preposterous, but hey, real physicists are taking this as a possibility. So let's break down the components. First of all, we know that the universe consists of galaxies. These galaxies consist of about 100 billion stars on average, and we see these galaxies everywhere throughout the universe. The nearest galaxy, for example, is Andromeda, which is 2 million light years from the planet Earth. It's a spiral galaxy. At the very center of Andromeda, there is a bulge, and in the center of the bulge, there's a dot, and that dot is a black hole. In fact, there are two dots there, meaning that at some point in the distant past, Andromeda may have had lunch. It may have eaten up a smaller galaxy, and as a consequence, two black holes merged at the center, and you see two dots, not one, but two dots rotating around each other at the center of the Milky Way galaxy. So it turns out that there is a theory that says that every galaxy has a raging black hole at the center, which means that our own black hole is probably at the center of the Milky Way galaxy. So if you want to see a black hole tonight, go outside, look in the direction of the constellation Sagittarius. In the area called Sagittarius A, there is a black hole. Now, by rights, there should be a gigantic fireball that comes out every night, and inside that fireball is the black hole. But what do you see at night? Almost nothing. Sorry about that. Dust. It turns out our galaxy is full of dust. As a consequence, when you look in the direction of Sagittarius, you don't see hardly anything at all, when by rights, you should see a fireball as bright as the moon. A fireball as bright as the moon rising every night, representing the center of the Milky Way galaxy. So our galaxy at the very center has a black hole that weighs about 2 to 3 million times the mass of our sun. So, given the fact that the galaxies of the universe are full of black holes, then the other question is, what's the relationship to the Big Bang itself? Well, that's where things get fuzzy, because the short answer is we're not sure. But there is a theory that says that when matter falls into the black hole at the center of the galaxy, it doesn't just disappear, it blows out the other end in terms of a wormhole. Now, back in 1935, it was Albert Einstein himself who came up with this idea. Think of a black hole as a funnel where everything falls into the funnel, nothing comes out. Now take two funnels and stick them back to back, so that when you fall into one funnel, you get blown out the other end of the funnel. This is called a wormhole, and it's an idea that Einstein considered very seriously, but of course he couldn't push it very far because we have no evidence. Back in the 1930s, there was no evidence of black holes, let alone wormholes and other kinds of things. So some people think that maybe the Big Bang is a wormhole, and we'll talk about that after the break. Welcome back to Science Fantastic Fantastic with Professor Michio Kaku. Once again, it's open mic on Science Fantastic. But where we last left off, we had a question that is at the cutting edge of physics research. What is the relationship between a black hole and the Big Bang? As we said before, black holes are found at the center of all galaxies that we know of. Matter falls in, we see that. These black holes eat up stars. In fact, we see pictures of our own galaxy eating up stars. But the question is, where do the stars go? Does the black hole have acid indigestion? Does the matter simply stay there, doing nothing, or does it blown out the other end? Well, as I mentioned, Einstein himself in 1935 came up with a solution where objects fall into a black hole and then get blown out the other end. And then in 1963, mathematician Roy Kerr found the solution of Einstein's complete equations, showing that if a single black hole rotates, it also has the same behavior. When you fall through a rotating black hole, you get blown out the other end. Then people have asked the question, doesn't that look like the Big Bang? So in other words, the black hole, instead of being the end product of stellar evolution, could it be the beginning? The beginning of a whole universe being created, being blown out the other end of a black hole? Well, the short answer is, I don't know. Nobody knows at the present time because we don't have enough experimental data. But yes, the answer to your question is yes, there is a theory proposed by reputable physicists that say that the Big Bang was essentially a black hole. Okay, let's move on now to the next listener phone call.
Hi, my name is Naveen Suresh, and I'm calling from Reading, PA. Hi, Dr. Kaku. I just want to ask a quick question. What exactly is the fourth dimension? And is it represented differently in the mathematical world versus the physics world? And is it possible in the future we could actually visit four-dimensional creatures? Thank you. Have a great day.
Well, you ask a question that has fascinated mystics, artists, philosophers for centuries. We know that the universe has three dimensions. We have length, width, and height. Given three numbers, you can locate any object in the entire universe. I live in New York City. When you want to meet somebody for lunch, you say, meet me on 42nd Street and 5th Avenue on the 10th floor. So three numbers locates a specific point in our universe. In fact, the entire universe can be summarized by giving three numbers, length, width, and height. But you see, there's nothing special about the number 3. Why should the number 3 be singled out when it's an ordinary number? From a mathematics point of view, there is nothing, I repeat, nothing so interesting about the number 3. Well, after the break, we're going to talk about hyperspace, about the movie A Wrinkle in Time, about tesseracts, about the fourth dimension after the break. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a question about the fourth dimension, and the fourth dimension is in the news. If you saw the movie A Wrinkle in Time, you realize that the gateway between our universe and these other universes is a tesseract. And what is a tesseract? A tesseract is a four-dimensional cube. So philosophers, novelists, science fiction writers have been fascinated by the idea of the fourth dimension. But what is it? Well, first of all, we know that our universe exists in 3 dimensions, length, width, and height. You can jump in 3 dimensions. You cannot jump in 4. And so then the question is, why? Why can't we jump in 4 dimensions? Now, your PC can easily calculate in 4 dimensions. Believe it or not, your computer is continually calculating in hyperspace, but you cannot move in hyperspace. Sorry about that. However, artists have visualized ways in which you might be able to visualize the fourth dimension. So let me explain. First of all, if I take a dot has no dimensions at all, but if I move it sideways, I get a line. So I added 1 dimension by simply moving a dot to the side. Then take this line and move it again perpendicular to itself. And what comes out? A sheet or a square. So when you move a dot to the right, you get a line. You push the line forward and you get a square. Now let's push the square. If you push the square in the third dimension, what do you get? You get a cube. Now push the cube. And then you begin to realize, oh, wait a minute, you can't do that. You can't push a cube in another dimension. But you get the idea that if you could push a cube into hyperspace, you could get a hypercube. Now, when I was a child, I used to go to the Japanese tea garden in San Francisco, and I used to watch the carp swimming beneath the lily pads, and I asked a question that only a child would ask. I asked myself, what would it be like to be a fish? I said to myself, what a strange world. The universe would be in two dimensions. I could swim forward, backward. I could swim left, right. But the concept of up into hyperspace, up into the world of the third dimension was considered impossible. And then I imagined a scientist fish who would say, bah, humbug. There's no such thing as a third dimension because the pond is the universe. What you see in the pond is everything there is. There is no world beyond the pond. End of story. Well, then I imagine one day reaching down and grabbing the scientist fish and then lifting him into the world of up, the world of the third dimension. What would he see? He would see beings moving without fins, a new law of physics. Beings breathing without water, a new law of biology. He would see worlds that are impossible in the pond. But then when I put him back into the water, what would he tell his fellow fish? He would tell them that he had a journey into the world of up, a journey into the third dimension, a journey into hyperspace, beyond our universe. There were unseen worlds, worlds upon worlds that he could only visualize mathematically, but there he was, moving in the third dimension. Now, around the turn of the last century, there was a book written about what would happen if a flatlander could move in the third dimension. So think about it for a moment. If you are three-dimensional and you could talk to people living in the second dimension, they would appear to you like cookie men that can only move in two dimensions. But what can you do? First, you can put them in jail. Jail consists of a square. You take a cookie, draw a square around it, and the cookie man cannot escape the square. A square is an airtight prison. But you, in the third dimension, can lift him up from the second dimension, and he could escape from jail by moving in the third dimension. He would literally disappear and reappear someplace else. And who has that power? Ghosts. So after the break, we'll talk about ghosts and the fourth dimension. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question that is quite profound, a question that has fascinated mystics, theologians, and even priests for over a century, and that is the fourth dimension. As we mentioned before, we live in a three-dimensional world, but if we could somehow move in the fourth dimension, we could perform magical feats. Think of someone looking down on a cookie man. A man who lives in two dimensions. If you draw a square around the cookie man, he's in jail. But to take him out of jail, you could lift him, literally lift him into the third dimension and plop him down someplace else. So how would it look like somebody in Flatland? It would look like you disappeared and reappeared someplace else. It would appear as if you could walk through walls, that the square of a jail cannot confine you, that you can literally peel yourself off the universe and land someplace else. Now, here was the question asked over 100 years ago. Over 100 years ago, the book Flatland popularized the world of two dimensions, and then people began to wonder about the world of four dimensions. Who has the ability to move between walls? Who has the ability to disappear and reappear someplace else? Well, the answer is obvious. Ghosts. And so back in the 1800s, late 1800s, there was a fascination with ghosts and the fourth dimension. Because anyone that moves in the fourth dimension would have the power of a ghost compared to the mortals who live in the third dimension. They would be able to walk through walls. They would be able to disappear, reappear someplace else, just like ghosts. Now, who else was fascinated by the fourth dimension? Salvador Dali. Salvador Dali was so fascinated by hypercubes that he drew one in his famous painting of Jesus Christ. Go to the web, look up the works of Salvador Dali, specifically Hypercubicus Crucifixion. There is Jesus Christ crucified in the fourth dimension. If I take a cube, for example, like a cardboard box, unravel a cardboard box, what do I get? I get a cross. 6 squares arranged like a cross. So a cardboard box unraveled in the third dimension becomes a flat 2-dimensional cross. So if I have a hypercube in the fourth dimension, and unravel it, what do I get? A 3-dimensional cross. And that's exactly what Salvador Dali painted in his famous painting, Hypercubicus Crucifixion. Jesus Christ crucified in the third dimension. So you see, the third dimension has fascinated artists as well as theologians writing about where ghosts are. In fact, theologians had a problem, and that is they believed in heaven, they believed in hell. But all of a sudden, with the discovery of the telescope and the space program, we began to look for heaven. And everywhere we looked with our telescopes, we could not see angels, we could not see devils, we did not see heaven or hell in outer space. And so theologians began to say, where is heaven? The answer, hyperspace. It would be a space beyond ordinary space. They would have magical properties of walking through walls, disappearing, reappearing, just like we can do when we meet Cookie Man in the second dimension. Now we have a revival of all of this because, A, scriptwriters are making movies like Wrinkle in Time about the fourth dimension, and string theory, which is what I do for a living, says that we live not just in 4 dimensions, but 11 dimensions. 1 dimension of time and 10 dimensions of space. In fact, if you saw the movie with Matthew McConaughey, the movie that talks about going through a wormhole into another universe, the movie called Interstellar, you realize that in the final scenes of the movie, Matthew McConaughey is floating a bunch of cubes, floating in air. And what is that? That is hyperspace. That is the fourth dimension. So here we have a situation where Matthew McConaughey and Hollywood have discovered hyperspace. Now, then the next question is this all theory and bunk, or is this really rooted in experimental reality? Well, the next question is, can you experimentally determine the existence of these other dimensions? String theory says that it's in principle possible, but in practice very difficult. These other dimensions have curled up to a tiny distance so that when we move, we don't feel the existence of these higher dimensions. They're there. We literally live in 11-dimensional hyperspace according to string theory, but you can't feel it when you move. Now, how do you test the theory? Well, some people have said that if the world is 3-dimensional, then forces diminish as the inverse square. If the universe were 4-dimensional, then gravity would diminish as the inverse cube. So here's a way to easily detect the presence of hyperspace. Simply calculate how gravity diminishes with distance. Well, that experiment was done in Colorado. In Colorado, several physicists created a small device that could actually measure deviations from Newton's laws of gravity in a room. Well, what did they find? Nothing. Sorry about that. What does that mean? That means that either these higher dimensions don't exist or there's no parallel universe in Denver, Colorado. I tend to believe it's the latter. I tend to believe that there are these other dimensions, but our instruments are simply not powerful enough to resolve them. So in other words, it's probably true that we live in a higher dimension, the dimension predicted by string theory, but our instruments are too feeble to prove it. Sorry about that. Good day.